So last day, we looked at Einstein's time dilation equation. In fact, we derived it cleverly with Pythagoras, complicated Pythagoras, but it was Math 8. And I tried to convince you that when objects are moving relative to other objects, time moves slower for the moving object. We call that time dilation. But there was some skepticism because many of you were saying, hey, I'm not noticing this. Put your pencils down, look up.
When Einstein realized that time elapses more slowly for an object in motion.
So this is Professor Brian Greene. He teaches at Columbia University, I believe. He's one of the world experts on special and general relativity. So he has a lot of very good explanatory YouTube videos. Let's talk about how fast does time dilation occur? How much does time slow down by?
And compared to the rate at which it elapses for us here on a stationary clock. He didn't just make a qualitative statement. He made a quantitative statement. He wrote down a formula that tells us how much more slowly time will elapse on that moving object. And if you like equations...
And who doesn't like equations?
The slowdown formula is 1 over the square root of 1 minus v squared over c squared. V is the speed of the object, c is the speed of light. But
that's that square root term that we found yesterday.
If you don't really like formulae...
How would you not like formulae?
Let me show you that equation in action just through some visual illustrations. So here is a stationary clock with us on Earth. Here's a clock on a spaceship. Now if the ship is not moving, the two clocks tick off time at exactly the same rate.
Are we all stationary relative to each other? We are all experiencing time at exactly the same rate.
But now let's give that spaceship some velocity. 1,000 miles per hour, reasonably quick speed. Notice that the slowdown, while there, is just too small for us to see it. That's why we don't know about the slowdown at everyday speeds that we can achieve. But let's take this 1,000 miles an hour and kick it up to a much higher velocity. 100 million miles an hour. About 1/6 of the speed of light, fast enough to go around the entire Earth in a single second. There is a slowdown on that clock. If you look really closely, kind of squint, you can kind of see it, but still, even at this very high speed, difficult to see.
But it is there. You can see the clocks aren't quite lined up anymore.
Not a big slowdown. So let's kick up the velocity of the ship even higher. Let's bring it to 600 million miles an hour. The speed of light is about 670 million miles an hour. Now, this speed, the slowdown of time becomes obvious, right? This clock is ticking off time much slower than our clock here on Earth. And just to see it even more starkly, let's bring that speed of the ship even higher. Let's put it at 668 million miles an hour, just below the speed of light. And look at how time is elapsing on the spaceship clock. Very slow compared to the rate at which time elapses on our ordinary clocks here on Earth.
Let's be clear though, you wouldn't notice anything if you were on that spaceship. Everything would be synchronized to that slower time, and so you wouldn't be able to tell that anything was moving slower. You would only find out that your time had been dilated when you reconnected, when you met the people back on Earth entering their reference frame, and you would go, oh, you guys experienced a different time rate than I did.
And this really illustrates quite wonderfully how we don't know about the slowdown in our bones intuitively because we never achieve speeds anywhere near the speed of light. But if routinely we did travel at speeds near the speed of light, this slowing of time would be obvious to us. This dramatic slowing of time near the speed of light would be intuitive. It would be in our bones.
So Why don't we notice special relativity in our everyday lives? Well, look at the time dilation equation. What was it? It was T equals T0 all over the square root of 1 minus V over C all squared. Could you write that down, please? I know it's on your green sheet, but we're going to dissect it just a little bit more. And Jaden, what I'd like you to do is circle the bottom part. I'll do it in red so you can see it a bit better. Circle the square root term. Ronan, that square root term, the square root of 1 minus V over C all squared, has a special name. We call it the Lorentz factor. It's named after a mathematician who, before Einstein showed why that's the case, Edward Lorentz was a mathematician who said, look, I don't know why, but if I plug this in, now the times match up. There seems to be this factor of 1 minus V over C all squared. That seems to do the trick. Don't know why, but it works. So we name it after him. And because we're writing that an awful lot, and we like to abbreviate, we use a Greek letter gamma. A Greek letter gamma is kind of like a fish doing a headstand, a really skinny fish doing a headstand. And so what you're going to start to notice is I'm going to replace the 1 minus V over C squared inside the square roots with a gamma symbol. And so I can write the time dilation equation as this, T0 over that, which is less writing, Liam. And I think I gave you that version on your green sheet. Can you double check? I think I said an equals T over little gamma symbol thing. Yeah, okay. I don't care which one you use. Should be right next to the time dilation equation, I think. That would have made sense to me. If you want to write the longer one because it has all the stuff in it, go ahead. If, like me, you tend to abbreviate, go ahead. And here's what I'd like to look at. I'd like to look at this square root symbol. So we're going to crunch how much will 1 hour of time dilate for each of the following situations. And what I mean by that is we're going to find out, draw a little line right here, T0. How would I get the T0 by itself? How would I get the T0 by itself? Okay, so we're going to go T times that square root thingy, all right? Where that square root thingy is 1 minus, okay. So let's suppose that one of you goes for a walk. 1 hour of our time will be how much of your time? Your time should be passing slower. So our time should be a bigger number. Let's crunch this. So I'm going to go, if you want to get out your calculator, okay, what's V in meters per second? 2. Unfortunately, it's not a percentage, so the C's don't cancel. What's C as a number on your green sheet? So on your calculator, go 2 divided by 3, scientific notation button 8. That's the V over C, and hit equals. You should all have 6.6 blah blah that. I don't know. Your exp or your EE or your times 10 to the, right? So that is that thing. What do I do? Look up. What do I do to that number? What's just outside the brackets? No, what's just outside the brackets? Squared. So go answer button squared and hit equals. And now go 1 minus. Answer button. And you get something weird. What does your calculator tell you the answer is?
1.
It's not 1 because 1 minus something can't be 1. It's so small, your calculator can't track the digits. So what's up? Let me go back. 1 minus, I got to put an extra one there. What's the time dilation factor for somebody walking? Really, it's so close to people that aren't walking, it's negligible. Let's go faster. Let's go in a race car. So now I'm going to go 70 divided by the speed of light. hit equals, hit my squared button, hit equals, 1 minus that, and again, Liam, we'll jump in the next one. Just have patience. Again, I get a 1. Is time moving slower on a race car? Technically. Is it calculatable? It's not a big difference. What about on an SR-71 jet? So an SR-71 jet is the fastest jet ever made. It flies at 1,000 meters per second, 1 kilometer per second. I don't know, let's find out. So Liam, you ready? You're going to go 1,000 divided by the speed of light, which is 3 scientific notation button 8. We're having to divide by 3 times 10 to the 8th because the C's don't cancel this time. I didn't give you a percentage. Hit equals. You got 3.3 that. Hit your x squared button. 1 minus that. So 1 minus answer button. Even on the fastest jet we've made, the pilots are not worried about, oh, I could come back and be younger than my child, right? What else moves fast? Faster than that? Let me pause. I'm seeing a lot of people staring at their calculators. Is it working okay? Yeah, working okay? Well, how about the Earth around the sun? The Earth moves pretty fast. The Earth is moving relative to the sun, which means time must be moving slower for us relative to the sun. So let's use this speed. Let's go 29,600 divided by 3 scientific notation button 8 and hit equals. X squared 1 minus that. Oh, okay, let's keep going. What's the next thing as we move out in the time dilation equation? What do we do with the 1 minus thing?
Around the galaxy.
No, what do we do with the 1 minus thing? Square root. So square root, answer button. Okay. For every hour on the sun, we age 0.9999. How many nines? 1, 2, 3, 4, 5, 6, 7, 8 nines, a 5, and a 1. 8 nines, 1, 2, 3. For every hour the sun ages, we on the Earth age 0.9999951 hours.
Awesome. That's so cool.
Ooh. The Earth is also, in our solar system, moving around the galaxy. So at the center of our galaxy, there's a large black hole. That means time must be moving slower for us than the large black hole. Let's try crunching that. So that's going to be 2.1 scientific notation button 5 divided by 3 scientific notation button 8. What do I hit next? Squared. Then what? 1 minus that. Square root. And so for every hour that goes by at the center of our galaxy, or every second that goes by at the center of our galaxy, or every year that goes by at the center of our galaxy, we experience 6 nines, a 7, and a 5, 5. 6 nines, a 7, and a 5, 5. Now let's go way faster. UBC has a particle accelerator, a cyclotron, where they accelerate protons to, well, you're getting closer to the speed of light. Speed of light is 3 times 10 to the 8th. This is 2.24. Okay? So 2.24 scientific notation button 8 divided by 3 scientific notation button 8 squared. 1 minus that. Square root. Okay, so what does this mean? That means if they want to do an experiment with those protons and they want the protons to experience if they time on their stopwatch 1 second, the protons have only experienced 0.665 seconds. And they have to take that into account, otherwise all of their calculations for particle decay would be garbage. They wouldn't work. So 1 second for the researcher is only 0.665 seconds or hours or years or days or whatever time you're using. One of the nice things about Einstein's equations is they're unit independent. If you put seconds in, you'll get seconds out. If you put hours in, you'll get hours out. If you put years in, you'll get years out. CERN, which is in Europe, gets muons to accelerate at 2.996 times 10 to the 8th meters per second. So let's crunch that one. 2.996, scientific notation button 8, divided by 3, scientific notation button 8, squared. 1 minus that, square root of that. For every hour that the researchers experience, the muons only experience 0.05 of an hour, about 1/20th of an hour. Or for every second that the researchers watch ticks, the muons only experience 0.05 seconds. At the SLAC, the Stanford Linear Accelerator, 2.9979, scientific notation button 8, divided by 3, scientific notation button 8, squared. 1 minus that, square root of that. The electrons age 0.037 seconds for every second that the researchers age, because the electrons are moving relative to the researchers.
What do you know?
That's time dilation. In fact, I can illustrate time dilation for you in 10 seconds. Would you like to see a video that illustrates time dilation for you in 10 seconds? It's also a physics joke.
This video would be 10 seconds long if you watched it while your computer was whizzing past you at 87% the speed of light.
So it's a 5-second long video to us, but if you watched it while your computer went whizzing past at 87% of the speed of light, you would see the video take 10 seconds, because for you, 10 seconds would go by even though only 5 seconds went by in the video. And under nerd trivia, bonus fact, the computer and spaceship would look blue because they would be blue shifted, because they're moving away from you, sorry, towards you. Red shifted is when objects are moving away from you. That's a Doppler thing. Nerd trivia. Well, I've talked about time travel. I've told you, all of you have traveled through time. So how can you travel through time? Here's 3 easy ways and 3 complicated ways.
Time travel can be complicated and complicating, so let's ignore all the paradoxical stuff and talk about a few simple ways that you can time travel without leaving your home. First, do nothing. You're already traveling through time. I mean, here you are, 15 seconds into the future since the start of this video.
So the first way is all of you are embedded in time. You're all automatically traveling into the future, but you're traveling into the future at the rate of 1 second every second. What you'd like to know is, can I travel into the future at a different rate from other people?
Easy, right? The point is, we're all always traveling forwards through time, but that's boring time travel. What's interesting is time travel relative to other people. To do that, start walking, and you'll travel through time relative to someone standing still. We've known for over a century that time and space are really just 2 components of a single space-time, and the faster you move, the slower time will pass for you. If you take a walk around the block, you'll be 3 femtoseconds younger than your friend who stayed home.
We tried calculating the time dilation for 2 meters per second. Our calculators couldn't handle it. You can find online what are called long number calculators. Put your phone away. You can find long number calculators and you can crunch that. That's the time dilation factor for somebody who's walking.
Except in order to walk around the block, you had to stand up. You're now further from the Earth, and so gravity is a tiny bit weaker for you.
General relativity, which we're not looking at yet, Einstein showed that gravity also affects time. The weaker the gravity, the faster time moves. The strong gravity slows time down. And so if you stand up, technically gravity on your feet is a little bit stronger than on your head because your head's a little bit further away from the Earth. It's a little bit closer to space. And so your head technically is experiencing time differently from your feet.
Which means you're traveling through time relative to your friend who's sitting down. That's right, more gravity makes time slow down too. If you stand up for a minute, your feet will age 10 femtoseconds less than your head.
Pretty negligible, but it's there.
On the other hand, GPS satellites high in orbit experience less of Earth's gravity and thus travel noticeably faster through time than we do, which is why their clocks are calibrated to run slow. But maybe you want to time travel more than a few femtoseconds.
Okay, so those were the 3 easy ways. Here's the more complicated ways.
Get ready for your head to start spinning. I mean, the universe. Because if the whole universe were spinning really fast, general relativity predicts there would be time loops all over the place. Moving along one of these loops, you'd always feel like you were moving forwards in time, but overall you'd loop around and travel back to a time and place in your own past. It's a little like how you can keep moving forwards on the Earth, but Earth's curvature brings you back to where you started. Unfortunately, our universe isn't spinning. Maybe it would be easier to build an infinitely long, super dense spinning cylinder, which would also curve spacetime enough to create a time loop. The problem, of course, is how do you build something that's infinite in size? Maybe you could just make it really, really big? No. If you tried to squeeze this time machine into finite space, you'd need negative energy, something nobody knows how to create, to make it work. Otherwise, you'd end up with a black hole. Wait, but what if instead of a black hole, we built a wormhole? Wormholes are hypothetical but not physically impossible bridges through spacetime, shortcuts that can instantaneously connect 2 different places and times in our universe. If you had a wormhole, you might be able to use it to travel into the past or the future. The problem is that no one knows how to build a wormhole, or once you've built it, how to keep it from collapsing. As Sean Carroll has eloquently written, keeping wormholes open requires a form of negative energies. Nobody knows how to make negative energies, although they occasionally slap the name exotic matter on the concept and pretend it might exist.
Or another word for wormholes, because most of you have heard the term wormholes. When the Marvel Universe started their movies, Thor travels from Asgard via wormholes, but they wanted something more exotic sounding. So another name for a wormhole is an Einstein-Rosen bridge, if you've watched it. It's a wormhole.
Well, that's too bad. But as a consolation, welcome to the future. Almost 3 minutes have passed since the beginning of this video, and we now have personal jetpacks.
So all of you have traveled through time in at least 3 ways.
Right now.
Okay? But can we do it more exotically? Maybe in the future. It gets weirder. Not only does a moving object's time slow down, it turns out if an object is moving, its length contracts in the direction of movement. I wrote here, the length of objects will be measured to be shorter when it's moving than when it's at rest. This shortening is only seen in the direction of travel. There's an equation for that. If the length of an object when it's standing still is L0, here's what I think. L0 equals the original length at rest. When you're at rest, what's your velocity as a number exactly? So L0 is original length at speed 0. If you're looking for a dumb way to remember what L0 means, that's what I do all the time. And L is the relativistic length, the weird length. It's really similar to the time dilation equation, except that gamma thing, the square root, isn't dividing the L0. What's it doing instead? And so another way you'll see this written is L equals L0 times gamma. Oh, I knew I had L and L0 down there. Sorry.
That's okay.
I was going, why didn't I put that in a little separate column? I usually would have. So there, I'll do that a little clearer. Okay? So let's take a meter stick. Here's my meter stick. And let's whiz it past us, going to your right at 99.5% of the speed of light. You would not see this with your Superman or Superwoman eyes, with your superhero eyes. What would you see? This says, how long would a meter stick appear to be if it was moving past you with a speed of 99.5% of the speed of light? What's this question asking me to find, L or L0? This is asking me to find the relativistic length, L. So let's go L equals question mark. So then what's L0? Here's your hint. It's a meter stick. Thank you. Some students just can't get that. I don't know. How long is 1 meter? 1. What's our speed? How will I write that in our notation? 0.995 c. So it's going to be L equals L0 times the gamma function, not divided by the square root. It's going to be 1 times the square root of 1 minus 0.995 c over c all squared. Do you see? Do you see? Do you see? What do you see? That's why I try and give you the speed as a percentage of light. In the earlier example, when I gave it in meters per second, we always had to divide by the 3 times 10 to the 8th, which is just a bit of a pain. What do you get? Sorry? 0.995? Really close to 0.1. So look up. This meter stick would actually appear to you to be only that long, but its height wouldn't change. So what you would see is all the writing smooshed together, really, really skinny. And there would be no experiment in your universe where this would not behave as though it was 0.1 meters long. In your universe, it would behave as though it was 0.1 meters long. So you ready? In your universe, it would fit inside a jar this big, just fine. In other words, if you had a tunnel, let's say about as long as my hands are, the meter stick would vanish completely inside the tunnel in your universe, even though if it's at rest, it will be sticking out of the tunnel from either end. Told you, the universe is weird and cool. Question? Yeah. Question?
You specified this universe. Does that imply
In-
that other universes?
It implies it's all relative. Your universe is relative to what you've decided as your reference point, what you're seeing. Okay? So you're at rest. You're not at rest. We're on an Earth that's moving. But if we decide that you're at rest and you're crunching the numbers for the universe mathematically where you're at rest, you would see that meter stick this long. Yeah. 0.09. You're right. There's a 0 there. 0.01. 10 centimeters is what it ends up being. No. Yeah, 10 centimeters. If I round off roughly, it's this. 10 centimeters long. 0.1 of a meter. Okay? An 85 meter long spaceship passes you at 2.23 times 10 to the 8th meters per second. Yeah. Am I wrong? I didn't crunch it. 998?
I don't know where you got the 5 from.
I don't know. I was listening to somebody.
But Ron didn't say 5.
Square root, answer button. 0.998? Let me try that again. 0.0998. No, 0.099 if I round off properly. Yeah, it's really close. Basically, by the way, if you're moving at 99.5% of the speed of light, the time dilation factor is almost exactly 10 to 1. 10 years go by on Earth for 1 year on the spaceship. The length contraction factor is almost exactly 1/10. An 85 meter long spaceship passes you at 2.23 times 10 to the 8th. How long does the spaceship look to you? What's this question asking me to find? L or L0? I think the spaceship's L0 is 85. I think this is L0. I think it's asking us to find L. So the original length at rest is 85 meters. Square root of, are the C's going to cancel this time? No. So I'm going to have to go like we did earlier, 2.23 times 10 to the 8th divided by 3 times 10 to the 8th. Don't forget the squared. Unfortunately here, do you see doesn't work. But okay, I got a good calculator. I would probably start with that mini fraction, 2.23, scientific notation button 8, divided by 3, scientific notation button 8, squared. 1 minus that, square root of that, and then times 85. When the spaceship is at rest, and the people that are on the spaceship, since as far as they're concerned, the spaceship is at rest, they would, if they ran a tape measure, they would measure the spaceship to be 85 meters long. But if you ran a tape measure really quickly as it went speeding by, you would measure the spaceship to be 56.9 meters long.
So, for example 1,
Yep.
if the meter stick was me, and I was moving past the meter stick with a speed of 99.5% of the speed of light,
Yep.
would I look
So you ready?
smaller?
Let's suppose you were in a spaceship and you went zipping by the Earth. Good question. And where our velocity is to your right. Okay? Now, if you're going even in our current spaceship speed, you're not going to notice a thing. But let's suppose you go faster and faster. Let's suppose you go at about 60% of the speed of light. You would see the Earth looking like that. Let's suppose you go at about 80% of the speed of light. 90% of the speed of light, 99%, and there would come a point where you would see the Earth looking like that. It would shrink in the direction of your travel, but it would not shrink in the perpendicular direction to your travel. Okay? Or,
It does.
if you traveled vertically,
Oh, it's wheel.
then you would see it shrinking in that direction.
It's like it's basically a cookie.
Okay? Here's the problem. It's all relative. You can also pretend that you're not moving, that your spaceship is at rest, and that space-time itself is collapsing in front of you. Remember yesterday we did that question where we traveled to a star and we measured the distance in light years, but then when the spaceship traveled, the distance was shorter? The reason the distance was shorter was space-time itself was compressing in front of them. The length was contracting in the direction of their travel. They didn't travel as far because space was shorter. Yep.
How would it go back to normal after being so flat? Like as you slow down, your acceleration.
It's both. It's all relative. So as far, if you're on your spaceship and you go zipping by, you would not be able to do a single experiment that would show that the Earth was a sphere. But the people on the Earth who are at rest, they don't notice anything wrong because they're not moving. They would see the Earth not distorted because relative to the Earth, they are at rest.
I know, but to you, how would the Earth go back to normal? When would it stretch back to the size of the normal?
As you slowed down, so let's suppose you were just doing a continuous loop. As you slowed down, as you slowed down, as you slowed down, as you slowed down, and then there would come a point where the Earth was normal, quote unquote.
If you came to a sudden stop, like in movies, you know how they
Can't do that because Einstein didn't know how to deal with acceleration yet. That's part of the issue, okay? So the other thing, you're asking questions that Einstein asked himself, and he's, I can't figure out how to work acceleration into this yet. All I can do is constant velocity. It took him 10 years after publishing his special relativity paper to work the acceleration in. He had to do tensor field mathematics. I've tried learning general relativity several times. I get about a half a page in and I'm lost. The math is well beyond me. And I'm pretty good at math. It's tough. It took an Einstein. Okay? So yeah, good questions, and they're answerable, but as soon as you try, if you want me to give you a good answer from special relativity, you're accelerating. The rules don't work. Sorry.
Oh.
So I wrote down here, what would the Earth look like if you sped past it near light speed? You asked the question before I got to it, but I thought it was a good segue. We're going to do example 3, and then we're going to pause for the day. So suppose a spaceship is 100 meters long when stationary. That 100 meters, is that L or L0?
L.
How do you know L0? If you're stationary, what's your velocity? Okay, this is the original length at rest, at speed 0. So I'll put a little L0 above there, as is my way of staying organized. When it moves past an observer, the observer measures the spaceship to be 25 meters long. I guess that's L. What's this question asking me to find? Is there a V equation on your green sheet with L's in it? Please tell me there is.
Yeah.
Okay, so V equals, and I know there's a C and I know there's a square root, but I don't know the rest. Oh, and I know there's a 1 minus. Is it L over L0 or L0 over L?
L over L0, and both L's are squared. But it needs to put into brackets.
Yeah, I do it that way. Okay. I'm going to leave the C as a C because that will give this to me as a percentage of the speed of light, and I like it that way. It's going to be the square root of 1 minus 25 over 100, all squared. What do you get as a decimal point what of the speed of light? And I really encourage you, try typing these in on your own because, yeah, this is fairly complicated calculator work. And you need to figure out how your calculator works and what shortcuts you can take. What was that? .968? 2? Let's go to 4 sig figs because we can.
9682.
So 96.82% of the speed of light would give you a 4-to-1 time dilation factor and a 4-to-1 length contraction factor. Okay. So we're going to pause here. But here's our thought puzzle. Look up. Suppose a 1 meter long spear, let's make it a meter stick, is thrown at relativistic speed near the speed of light through a pipe that's 1 meter long. Both these dimensions are measured when each one is at rest. So these are both L0s. When the spear passes through the pipe, which of these statements best describes what is observed? A, the spear shrinks so that the pipe completely covers it at some point. B, the pipe shrinks so that the spear sticks out from both ends at the same time at some point. C, both shrink equally so that the pipe exactly covers the spear at some point with no extra room. Or all of the above, depending on the motion of the observer. Yeah.
All of the above.
It is. It's all relative. So you ready? If you were sitting on the pipe and you had Superman eyes, since you're at rest relative to the pipe, you'll see the pipe 1 meter long. You'll see the spear shorter. If you were sitting on the pipe, you would see that, the spear inside with room to spare. If you were sitting on a spaceship zipping by, you could see, if you were sitting on the spear, as far as you're concerned, the spear isn't moving. What's moving? The pipe is moving towards you. And so you would see the pipe really short, and the spear sticking out on either end at the same time. Okay? The third one, if you see them both shrink, that would be if you were observing from the side and they were both moving at relativistic speeds, you could see that at the same time. Do you notice I keep saying at the same time? How is that possible? Because time is moving differently in all three of those situations. And so situations that person A sees happening at the same time, person B would not see happening at the same time. They would see them happening at different times, but it's all relative. This is the universe that we live in. Nothing really happens at the same time. It all depends. Put your pencils down. This will take us to the break.
The speed of light is meant to be the ultimate speed limit in the universe. According to Einstein's special theory of relativity, nothing should move through space faster than light. But that doesn't stop people from trying. Every day I get a lot of messages proposing ways to go faster than the speed of light.
I can see Ronan just sending email after email to Derek. Ask, wouldn't this work? So you ready? Here's some of the suggestions.
There is the classic method where you shine a laser at the moon. If you can flick that beam across the moon's surface in less than 1/100th of a second, which is not hard to do, then that laser spot will actually move across the surface of the moon faster than the speed of light. Imagine what that would look like if you were standing on the moon. If you were quick enough to perceive it, you would see this laser spot move faster than the light coming out of your own laser. How is that even possible? Well, in truth, nothing here is really traveling faster than the speed of light. The individual particles of light, the photons coming out of my laser, are still traveling to the moon at the speed of light. It's just that they're landing side by side in such quick succession that they form a spot which moves faster than the speed of light, but really it's an illusion. Nothing is actually going faster than the speed of light, so you couldn't transmit any information this way. Dan asked, what if instead of a laser we used a long rigid stick instead? Now surely if you flick your wrist, the tip of the stick must move across the surface of the moon faster than the speed of light. Well, unfortunately, this won't work either. As we learned in the Slinky Drop experiment, the fastest a force can propagate through an object is the speed of sound. That's because each atom needs to bump into the one next to it to transmit that force. And this is a lossy process. So you'd be lucky if any of the energy you put in at the start actually made it to the tip. You'd be lucky if the tip moved at all. Now this is a really sophisticated idea. Girard writes, a very special space-age engine would need to be designed that is capable of doing 10,000 plus RPM in outer space with very high torque. Consult Elon Musk for this. As the engine is spinning, it slowly deploys two very long tethers made from carbon nanotubes on opposing sides. Eventually, each carbon nanotube tether reaches an amazing length of 285 kilometers. At this point, the end of the tether will be traveling at the speed of light. Can you point out some reasons as to why it would not work? Yes, Gerard, yes I can. First, any object going in a circle requires a force pulling it in towards the middle of that circle. That's called centripetal force, and you can feel it when you whirl a ball above your head. Now, that force is dependent on the speed of the object squared. So if that gets to be too great, the tether breaks. Now, if you had a single gram rotating at 99% the speed of light, the amount of force required to pull it towards the center would be 300 meganewtons. That is the weight of 6,000 fully grown African elephants. But you're right, carbon nanotubes are tremendously strong. If you had a fiber just 8 centimeters wide, you could support all of that force. But now the problem is, if you have less than a centimeter of that fiber, it adds another gram to the tip of your tether. And so now you need a thicker fiber in order to support that additional force. And that would happen all the way to the base. The fiber would need to get thicker and thicker and thicker all the way back to the motor. And if you do the calculation, you find that basically 30 meters from the tip, the fiber already has to be as wide as the observable universe in order to support all of that force.
So you're not going to get 285 kilometers if 30 meters in, you already got to be wider than the observable universe.
It's nuts. But it gets worse. As an object moves faster, its inertia actually increases. That means it requires more force to accelerate it. In fact, that 1 gram mass going 99% the speed of light would require 7 times the amount of force we calculated before. And so the tether would have to be even thicker. But things get even more problematic if you think about speeding up the tip of the tether that extra 1% to the speed of light. I mean, since the inertia keeps getting greater and greater, it requires more and more force to accelerate it. And in fact, to speed it up that extra little bit to go the speed of light would require an infinite amount of energy. Okay, well, putting the infinite energy aside, let's say we could create an incredible motor and we could find a material much stronger and lighter than carbon nanotubes. Is it at least in principle possible that the tip could go faster than light? No. There is one final problem which is insurmountable, which is that a tether, like anything, is held together by the electromagnetic interaction. That is, the attractions between all the tiny little charges that make up the material. Now the problem is, electromagnetism is a force carried by photons. I mean, the way that something knows that another thing is there to attract it is by the exchange of photons, these force-carrying particles. And the problem is the photons themselves move at the speed of light. So even if you could create this incredible apparatus with ridiculously strong materials and spin it up with infinite energy, it still wouldn't go the speed of light. Because the force-carrying particles that hold the whole thing together only go the speed of light. The speed of light really is the ultimate speed limit in the universe.